Let's welcome Michael Kölle, Learning from the Past, Crowd-Driven Active Transfer Learning for Semantic Segmentation of Multi-Temporal 3D Point Clouds. Thank you.
Yeah, thanks for the kind introduction. Yeah, our work is about crowd-driven active transfer learning for multi-temporal point cloud classification. So a lot of buzzwords mentioned in there, but in what way are they all tied together for our task? Yeah, well, as soon as we have acquired airborne data, such as a laser scanning point cloud, often we would like to derive a semantic segmentation by some kind of supervised machine learning model. Yeah, so for instance, the colorized point cloud at the top is to be transferred to the semantically enriched representation at the bottom. But however, the requirement for this is to have some proper training data, which can be very time-consuming to collect. And this is why we would like to limit labeling to only some most informative points, like shown here in the middle. Yeah, and this is where active learning then actually comes in. But additionally, we don't really want to label those points by ourselves, yeah, even if it's just a few. But we would like to ask the crowd to perform this tedious labeling task for us. Okay, so suppose there is a way of combining crowdsourcing with active learning to come up with a reasonable semantic segmentation of a given point cloud. Yeah, but what happens if there's a new but related point cloud? Do we have to start again our workflow from scratch? Or is there a way to make use of information that is already available, that is already learned? Yeah? So our task at hand is semantically interpreting multi-temporal data. And this leads us to the question where to get training labels from and how do we deal with multi-temporal data in an efficient manner. And as already mentioned, the first issue can be solved by crowdsourcing. Yeah, so this means that an expert or a small group of experts who typically perform this labeling task is replaced by the crowd. And for hiring and managing the crowd, respective platforms such as the microworkers platform can be used. Yeah, so this means we are doing paid crowdsourcing where each crowd worker receives some small amount of money for his work. Okay, but still we need to find a way to label multi-temporal data in an efficient manner. Yeah? So consider over time we capture a specific area multiple times. And basically this is what national mapping agencies do all the time, and this is also what is visualized here. Yeah, so we have 3 different epochs which all depict the exact same location, but of course they differ in terms of changes in object space, phenological changes, the atmospheric conditions such as lighting are different, and in our case on the right also the acquisition method and thus the resolution of the resulting point cloud is also different. But nevertheless, the underlying geometry is pretty much the same. And this is why we assume that if we have already trained a classifier based on one of those epochs, that we can reuse at least a small portion of information that we don't want to waste. Yeah, and for this, we use an active learning pipeline, which is designed to transfer a classifier for successful classification to another domain, and where labels are given by crowd workers. Okay, so now let's focus on how this pipeline works. We start with a completely unlabeled point cloud, which we assume to be our source domain, and which we present to the crowd. And now we ask each crowd worker to identify one point for each class we desire, for each class which is to be automatically identified in the end. And by this, the crowd is building up some sparse initial training data set. And this data set can then be used for training a machine learning model, which might either be a feature-driven random forest classifier or a CNN approach. And within this work, we focus on a random forest classifier. And by usage of such a model, we can then derive a first semantic segmentation for all remaining data points so that we could potentially already stop our workflow there. But of course, if we aim at higher accuracy results, we need to continue our workflow. And therefore, the second and even more important task of our classifier is the detection of most informative points. And only those most informative points are then presented to the crowd for labeling. So this means we focus manual labeling effort on only those points that are worth it. And by this, we iteratively enhance our sparse training data set, and we repeat this workflow for n times or n iteration steps to form our active learning loop. Yeah, okay, but how can we design such an active learning concept to switch from a source domain to another domain, the target domain? And the easiest way to do this is to just switch the selection of most informative points from the source to the target domain. And again, only those points are then presented to the crowd for labeling. And therefore, we gradually enhance our sparse training data set by most informative points of the target domain, but still all previously sampled points from the source domain are still present. But we could also argue that some source domain samples are no longer representative for the target domain. So for instance, consider vegetation points which might be colored yellow in fall but green in spring. If such misleading information is not eliminated, this might lead to a delay in the convergence of our active learning loop and thus to increased costs compared to an active learning loop which was started from scratch on the target domain. And the elimination of such source domain samples can be achieved by measuring the disagreement between two classifiers, where one is trained solely by source domain samples and the other one by the combined training set of source and target domain samples. Okay, so what is a practical application of this concept? There is the Hessigheim dataset, which offers multi-temporal point clouds. And we start with an epoch or with a point cloud, which was captured from an UAV in spring and which we assume to be our source domain. And there we have a pretty realistic depiction of color since we had pretty good flying conditions there. And for this epoch, we launch a basic active learning loop, and we would like to transfer the resulting classifier, or more precisely, the underlying training set to another domain. And for the first scenario, we would like to transfer our classifier to another point cloud, which was captured in fall. And their vegetation has greatly changed for sure, but also fog affected and kind of distorted our multi-ego readings. And for the second scenario, we would like to again transfer our classifier from the source domain, but this time to a much more sparse airborne laser scanning point cloud. And since no concurrently captured imagery was available there, the colors were just obtained from an orthophoto, so that we are more or less dealing with a 2D colorization. So two different scenarios, and we will see whether our transfer is suitable for minimizing labeling effort by leveraging existing information. And for the beginning, we ran some experiments where we just simulated the crowd by drawing labels from the reference set before actually employing a real crowd later on. And for both scenarios, we ran a series of baseline solutions. And here the dotted black line represents the result of passive learning, where we were using the completely labeled training set of the target domain and used that also for prediction on the target domain. And we compare it to an approach where we are using the completely labeled training set of the source domain and use that one for the prediction on the target domain. And this is what we call passive transfer learning. And the greater the gap here between those two black lines is, the more severe is our domain gap and the less helpful source domain samples are. And in case of the second scenario, we are dealing with quite a significant domain gap, so that there we should be content if source domain samples are at least not harmful for the classification process. And then we started with a pure active learning run on the target domain. And as we can see, we can reach a level of accuracy similar to the one of passive learning while significantly reducing our labeling effort. So our transfer should perform at least as well to be useful. And this is the result of active transfer learning, where we are just merging source and target domain samples into one common training data set. And as we can see, for the first scenario, it behaves quite desirably since we directly start on a rather high level of accuracy, and we are about 3 iteration steps ahead of our active learning baseline. But for the second scenario, things are a bit different, and although we can surpass the result of passive transfer learning, we do not reach the same level of accuracy as our active learning baseline in the end. But if we now eliminate source domain samples that are no longer representative for the target domain, then in the end we can reach the same level of accuracy, and still we could avoid generating an initialization data set for the target domain so that codes could still be saved. Okay, coming back to our crowd-driven pipeline, where we would like to replace labels from the reference set by crowd-generated labels, and where the crowd might use a tool similar to the one displayed here the labels we obtain are always a bit imperfect. Yeah? And as we can see, the accuracy of the crowd varies quite a bit. The mean is about 86%, and we can also see a trend of decreasing accuracy, which is due to sampling more and more complex points in the course of the iteration. But good news is that if we compare the accuracy curve from before, which is the green line here, and which relies on ground truth labels, to the one using a real crowd oracle, then results differ only insignificantly. Yeah, so to summarize, it is possible to come up with a pipeline where an expert labeler is completely replaced by the crowd, and the labeling effort is minimized by both active and transfer learning techniques. Yeah, and also I would like to take the opportunity to promote our multi-temporal H3D dataset, which is really available as a new ISPRS benchmark. So thanks for listening.
Thank you very much. And we have a few minutes for questions. Okay, we have one.
Thank you for the nice presentation. I was wondering, maybe you told it and I don't get it, but how do you choose the most informative points?
Yeah, I didn't cover that. Yeah, that's true. The selection of most informative points is based on the uncertainty of our current classifier. Yeah, so in each iteration step, we have this training data set, and we use it to train our classifier, and then we have him predict on all the remaining data points. And the uncertainty is then measured based on the entropy of the a posteriori probabilities for each point, and we would like to sample the points having the greatest uncertainty. But since we are doing batch mode active learning, so in each iteration step we are sampling more than one point, we also need to make sure that the points we select are as diverse as possible, which is due to efficiency and to boost the convergence of our active learning loop. So we also try to do this, and this can be done by k-means clustering of the feature space, and then we select one point for each of the clusters.
Thank you.
Do we have more?
Thank you for presentation. I have a question that when will you decide what is the criteria when you decide to update the active labels in each training iteration, and when will you end the whole training process?
You mean how do we select the points? Or?
Because the active learning is a loop, iterative process, and
yes.
You will keep update, add extra labels and training the model, and in each training iteration, when will you end the training, and then you choose to select more labels?
Yeah, actually what we do is after each iteration step, we compare the predictive result of our classifier to the previous epoch. And if those two classifications are close enough, then we decide to stop our workflow. So we need some threshold for the stopping criteria, and this is how we stop our iteration.
Okay, thank you.
So we have time for one more small question. Right. So I have one. So how do you? Very simple actually. How do you think of how cooperative you think the crowd would be if you apply that to the real case scenario?
We did apply to a real case scenario. Okay. So our campaigns were posted on Microworkers, which is a platform for paid crowdsourcing. And we paid 10 cents for each crowd job, and each job consisted of 10 points. And so the campaigns did run in a real world scenario.
Okay, great. Thank you so much.